Cool. So actually, I'm going with Anil's suggestion. So he suggested that, so we have two papers. I'm going to give a brief introduction to both of them in this talk. And then in the next session, I'll give more of a demo of various things. Um, so to give a bit more context, in all of our work, we're very driven by understanding what problems or what questions our community is really trying to answer. So that kind of informs what eventually computational problems are we ending up solving. So we do a lot of field visits in rural areas, in different parts, and just to give some idea, right? These are examples of farm ponds. This one is what's called an unlined farm pond, which essentially collects rainwater, and then all the farm fields close by, they benefit by way of improved soil moisture and so on. But this one, what you see is a lined farm pond, where the use is very, very different. Here you actually pump water from the ground, yeah? And you store the water and then use it for irrigation. So the kind of questions when it comes to an NGO trying to do some planning, right? This one is basically trapping surface water and sort of preventing runoff going further down. But this one results more in groundwater depletion, right? So how many such kind of structures can a landscape support? And then likewise for a farmer, yeah, that if I were to do a farm pond, where currently I'm doing some cropping, so I'm going to take away that land and put a farm pond over here, how will it actually benefit me? How many weeks do I think this farm pond will hold water? Yeah, those are kind of micro questions. Likewise, some other things where there's a lot of room for informed scientific planning to start happening. Fields in downstream areas where the upstream areas are forested, those fields get a lot of very high nutrient runoff. Because this water coming down from the forest that's rich in soil organic carbon and everything. But many of these traditional systems have sort of gotten sidelined. People rely more on synthetic fertilizers than kind of natural runoff and so on. So, you know, those are the kind of things that there's a lot of scope for improvement in, and in some ways, you know, going back to traditional systems that were out there. Likewise, you know, questions like if I want to do more commercial cropping, right? How much area can I bring under sugarcane plantation, right? Or not me, right? But for the village as a collective to answer, right? How much, you know, area under commercial cropping should we actually have? So that's really the kind of things we're trying to answer. And there's like a rough categorization, right? That when it comes to computationally solving some of these, then what are some of these questions, right? So a lot of the work currently that we see happening around us sort of revolves around pixel-based things, where largely you essentially have a mashup of different raster layers, where you want to sort of combine one raster, take its output, put another layer on top of it, and sort of like identify, right, which forest patches have seen some kind of degradation. And those areas become important for restoration planning. Yeah. Some more, in fact, the GeoBond talk was talking about building indicators, right? So this is slightly more complex, where you start using some raster layers and sort of figure out, okay, which particular areas or hydrological units are more, let's say, drought prone than others. And in those areas, is there also a lack of surface water availability in those areas and so on. So these, again, are helpful for planning purposes, that which particular areas can benefit from you know, different types of interventions. Yeah. But what we also need is a lot of coupling with hydrological models. And here again, there are different approaches. Right? So in this pixel-based category, what I've put down is what civil engineers do a lot of basically finite element simulations to understand how groundwater flow or surface water flow is propagating. So again, these kind of things can be important, right? That if you were to do a particular plan, right, come up with some new check dams or gully plugs, right, what particular area will really benefit? And then more complex stuff, right? So some of the things we were, in fact, just talking about over lunch, that can you divide a particular landscape into different units and say that, well, if I were to do afforestation over here and come up with new water bodies in some areas, right, how would it impact cropping? So this really, right, you're representing the landscape in terms of units and figuring out what are the connections, what's the nesting of these units, and then you can do all sorts of different ML models on top of it. the two papers that I'm going to talk about, right? One is about figuring out that in these kind of use cases where you're talking a lot about raster layers and coming up with indicators on different spatial units and everything, there's a big problem of data and algorithm management. Actually, what the GeoBond talk was really talking about. And in this part, there's a big problem of scaling, right? That the more micro you go, how do you really do faster computations and right at this very high resolution? So coming up with this first part, right? This is an example of a data flow graph in the setup that we're trying to build called the core stack. So basically, there's some raw data that you start with on which you apply some algorithm that produces some other output and so on. Yeah. Now the problem is that if let's say we were to update an ML model somewhere, right? We have now new ground truth, we update the model, then you want to recompute all the stuff downstream. But again, maybe you don't want to recompute everything, but you want to have some sort of determinants that if the outputs at some point are not differing a lot from the previous version, then maybe don't compute, yeah? But also figuring out version management, right? That for any particular data set that you've produced over here, what's the lineage? What version of the algorithm actually ended up producing it, yeah? So you want to maintain all of that information in some way. One of the main standards for data sets is the stack standard, spatial temporal asset catalog, yeah? So again, it's very straightforward. Basically, you talk about, right, what's the resolution, what's the projection system, and a couple of other things, right? But there is really no scope for maintaining lineage information. The only one field which is kind of there is a derive from field. But in fact, we failed to find even one stack standard where this was populated. So what we're proposing is just something very, very simple. Basically, we're saying that let's think in terms of a representation of a DAG. So this DAG has some parameters on which you want to execute that whole DAG, right? Parameters could be like the area of interest or some years on which you want to run that whole DAG. Now, what this DAG does is that is basically a sequence of algorithms. So you know what algorithms and input data sets are needed. There's a description of the algorithm that what inputs is it going to use. And there are versions of the algorithm implementation. So you can keep, what you want is that you keep updating the algorithm without sort of fundamentally changing what it's meant to do and without changing the input and output formats and sets, but you want to update different versions of it, yeah? And then likewise, these basically then produce ultimately different data set instances. And this is basically what's this you want to put into a stack. This is basically your stack item actually. But behind the stack item, you want to maintain this whole machinery, yeah? So, so this is what we've done. We've basically come up with a simple YAML representation of the DAG. And we've also done a reference implementation in Airflow. Apache Airflow is an open source workflow orchestrator where you can basically give it a DAG and then it executes the DAG, right? And it takes care of the sequencing of operations and dependencies. So basically what this does is that it takes the YAML configuration and then Airflow internally requires the output, the DAG to be coded in a particular format. So there's a converter which basically converts it. And then this Airflow can then trigger different kinds of computes. So one thing that we've implemented is basically that the algorithm instance is described in terms of Docker parameters, right? So what's the Docker image and mount points and everything, and then it executes that. Similarly, there's another with API-based things that the DAG can invoke an API. This API in turn, there could be something which goes to Earth Engine, computes stuff, and brings it back. And then all of this is maintained in a database. Yeah. So, and on this, we've also implemented a couple of simple things like full exec is, it executes the entire DAG on the particular set of inputs. Algorithm update is where some particular algorithm in the DAG is updated, and then everything downstream of it gets recomputed. Similarly, dataset update, DAG augment, that you can augment the DAG with more nodes and edges, and internally we figure out, right, which ones need recomputation, and we recompute. Then some more things that will be very interesting, right? We're trying to work on these things, right? Define how far should this recomputation progress, right? Based on whether the data sets, the outputs are sort of differing more by a particular delta, or what the geobond talk was also talking about, right? If the algorithm is, through static analysis, if you're able to figure out, right, if this is very different, then maybe you then trigger a recompute. So that's the stack work, and I'll change gears and also briefly introduce, right, the other kind of problems that we're trying to solve with doing faster algorithms for these kind of hydrology simulations. Yeah. So here, the main purpose really is that there are these hydrology simulators like, sorry, what's the major one? It'll come back to me. But they don't sort of operate on very fine timescales like ours. Rather, it's daily kind of temporal updates that they do. Or the spatial units that they consider are quite large, 1 km square or larger, and not like a pixel level, 30-meter sort of a resolution. So, and largely they're all CPU based. So that's really where there's an opportunity to recode many of these algorithms. So one of the things that we wanted to do is basically simulate runoff, that when it rains in a landscape, how does the water flow? And there are different, the civil engineering folks have all sorts of numerical methods of figuring out that if it rains and based on the past rainfall, how much water will infiltrate, how much will run off, and they take the soil type and all sorts of things into account. And based on that, you want to recompute, yeah? So, so in a given landscape, where there are, this is represented through a digital elevation model that the elevation of each pixel. These are 30-meter pixels which are out there. So on this, now when it comes to this runoff computation, you of course first have to compute the flow direction. And here, one of the simple algorithms basically just says that the water will flow down the path of steepest descent. So this is now a straightforward operation which is easy to parallelize, basically a short pixel operation, right? Because on each pixel, you're basically seeing its neighbors, yeah, and seeing that for this pixel, therefore, what is the direction of steepest descent? And it's similar to a convolution operation, right, which is easy now to parallelize on a GPU, yeah? The harder part happens that you then have to run an iteration that where will this water flow eventually, yeah? So this is now an algorithm called flow accumulation, but that is sort of unbounded, right? Because it can keep propagating up to sort of the length of the path over which this propagation will keep flowing. So this is a long pixel operation, and that is harder to parallelize. So this is basically just a trick that we came up with, which I'll talk about of how we do that, yeah? Then there's more complex stuff that you do, that once you have the flow accumulation, you define a particular threshold, and anything above the threshold are what are called drainage lines. So basically what happens is that these drainage lines are where more flow is accumulating. So once you threshold, you actually come up with the path along which the water will travel, yeah? And then there's cool stuff that happens after that, right? You find out which of these are head streams. They're called stream order 1, and then 2 streams of stream order 1 will combine together to produce a higher order stream, and eventually you end up in a river, and the river goes into the ocean and so on, right? There's other things that are also done, which is used for the hydrology folks talk in terms of hydrology units of watersheds and micro watersheds. So here again, they basically take points on these drainage lines and they figure out that on this point, what is the catchment that is flowing into that point? So this becomes a micro watershed. And so again, these are basically different versions of long pixel operations, and you eventually break up a particular landscape into smaller units. And these units are easy for analysis because basically what happens is that whatever rain is kind of falling in one unit is sort of constrained in that. Yeah, there's one outlet point from that. And then it is on this that you then do your runoff accumulation. That basically you look at your rainfall, what is the land use, the soil group, and the slope, and this is and the rainfall, and it's based on this that there's a lot of numerical models which then give you what is the per pixel runoff expected, and which then has to propagate along the flow direction. And eventually you want to come up with these kind of what are called hydrographs that along some network of points on which the major water will flow, how much meter cube per second of water is going to flow. Yeah, so this is basically then this becomes important for flood modeling and all of that. So the reason to do it at a microscopic scale is kind of, right, like I was saying, to answer those kind of questions that even if on these small order streams, if somebody were to do a check dam, then the farmers are interested to know that if a check dam were to be done here, will my fields not get waterlogged? Yeah, or if a water body were to be rejuvenated, then what's going to happen? Yeah. So now on GDAL, many of these are CPU based, so they take time. Platforms like Google Earth Engine don't support long pixel operations, and the biggest, this you might even be able to compute statically because this is not changing. But with runoff, if you want to do it on a hourly basis, right, then that becomes a killer. So that's where it's a simple trick that we did. Basically, what we do is that on a particular, right, for each of these pixels, we figure out what is the velocity on which, with which water will flow, and then in a given time step, you can sort of know that, okay, this pixel in 1 second will go where? Yeah, the water that is generated as runoff from this pixel, where will it go? And we use this to build a jump matrix, basically. Yeah. So what then happens is that this long pixel operation essentially becomes a lookup operation. Yeah. That this is just a row major indexing of the pixels. So what you can then determine is that the pixel over here, if some runoff is generated at that pixel, which other downstream pixel will it go to in 3 hours? Yeah. So this basically simplifies the problem, right? That now you don't have to do the whole iterative computation, right? But now it's basically just a lookup operation, and which you can then do on a quick basis. Yeah. So this is just, right, the area that I was showing is this particular area, and this is the much larger, what's called the lower Ganga basin. So what we're actually able to do now is that on this large area, 250,000 square kilometers, this is rainfall, and we're able to do the simulation on 30 meter pixels. Yeah. So this helps in that. There's a lot of other stuff which is also happening in the broader ecosystem around not just using these process models, but think about machine learning methods to do that. Yeah, so I'll stop here and yeah, take questions. Yeah.
Questions? Questions? If you have questions, please come over to the mic.
Thank you very much, Adi. That was great. I had a question about the adding the DAGs for the having the algorithms within the stack. I was wondering if there was ways to add things for reproducibility. So whether you kind of have these things that allow you to say, you know, this data has changed and rerun stuff. And I was wondering if there could be some automated kind of tooling to decide that this data has changed because the hash has changed or this algorithm has changed. This hash has changed. This Docker image is no longer the same Docker image, it's being pushed and it's a new one, of these sorts of things to try and bring some reproducibility into that.
Yeah, no, I mean, very, very useful, you know, this is just very, very early work. We've still in the process of building, but, you know, there's a lot of scope to build further tools and everything on top of that. Yeah.
Iterating on this technology will allow for things like flood prediction, or will that require
No, I mean, that's something we want to investigate. Largely for things like flood prediction, mostly using these kind of process models, lower resolution simulations have been done. And then they're kind of compared with machine learning driven methods that are able to learn many of these features. So it'll be interesting that now that we can do higher resolution stuff, are these process-based models able to do better? So that's really one of the next steps in this.
Excellent. Let's thank the speaker again.